In this first video of several for Chapter 12, we're going to start talking about functions of several variables, and we're going to first do that by talking about partial derivatives. So let's look at a function p equals rt over v minus b, and let's identify, p equals rt over v minus b minus a over v squared. The lowercase a and b are constants, and p is pressure, t is temperature, and v is volume, and also the r here is a universal gas constant. And so first we're going to take the partial derivative of p with respect to t. Take a partial derivative with respect to one of two or more variables occurring. We want to note that everything that is not that variable is considered to be a constant. So I'm going to circle r over v minus b and note that that is a constant, and I'm also going to circle all of this. Since there's no t in there, that's also a constant. Or it's acting like a constant. It's not really a constant, but we treat it that way when we take the partial derivative with respect to t. So we have separated off the r over v minus b here in front of the t, and now we're going to take the partial of p with respect to t. And so over here in this first term we have effectively a constant times t that we're taking the partial of. And so partial p partial t is just that constant r over v minus b. And then when we go to take the partial derivative of this term right here, everything is a constant, and so we've actually got the partial derivative already right here. So that's the partial of p with respect to t. Now on the next blackboard, let's take the partial of p with respect to v, which is a little bit more complicated. Here we have rewritten p in the p formula, and we're going to take the partial of p this time with respect to v. Well, v occurs in both of these terms, and it actually occurs in the denominator of both these terms, so we actually have to use we're not able to take any shortcuts and remove constants. We should however we can rewrite p, the first term of p, to make it a little easier. So it would be rt v minus b to the minus 1, and then r v to the minus 2. So what we've done actually is we have separated the constant here in this part, although the constant is wrapped up with the v in this case. So we're going to use chain rule in the first term and the simple power rule on the next term for taking the partial. So partial p partial t is, and we just have a constant here, rt, so we're going to multiply this power, bring this power down, so it's minus 1 rt v minus b to the minus 2 power times the derivative of the inside with respect to v. Corrected that right here. This should have been partial p partial v. And now the inside, the derivative of v minus b with respect to v is just 1, and then we go to take the derivative of this term right here. We bring the power down, and so that's 2 r v to the minus 3, and then rewriting in a more succinct form we have this. So looking at these two partials, here's the partial p partial v, and then back over here, here was the partial p partial t. We can see that they're quite a bit different. Let's go to the next blackboard to look at what a partial derivative means. I'm going to show that a certain function v satisfies this equation, which is called Laplace's equation. Laplace's equation is just the second partial with respect to x plus the second partial of v with respect to y plus second partial of v with respect to z added together equals 0. So the function v that we're going to work with is going to be x squared plus y squared plus z squared raised to the minus 1/2 power. So let's calculate v sub x, the partial of v with respect to x, and notice that we would use the chain rule, so we bring the power down, we leave the function that's in there, x squared plus y squared plus z squared. We reduce the power by 1, and then we multiply by the derivative of the inside, but only with respect to x. All of the other terms inside are treated as if they are constants, and so we just get the derivative of the inside is 2x. If we rewrite that, we get negative x over x squared plus y squared plus z squared raised to the 3/2 power. So that's this expression right here. Now in calculating v sub xx, we are going to use the quotient rule, and we'll do that on the next blackboard. So we're going to write that second partial with respect to x as v sub xx, and we're going to use the quotient rule, denominator times the derivative of the numerator minus numerator times derivative of the denominator over denominator squared. So let's write out what those expressions are. So going through and identifying the parts, here is the denominator, here is the derivative of the numerator, here's the numerator, and everything here is the derivative of the denominator, and of course this denominator here is the preceding denominator squared, the power 3/2 squared becomes the power cubed. Now if we clean that up in the numerator, so let's notice that this term here and this term here have as a common factor x squared plus y squared plus z squared to the 1/2. So we have factored that out. And when we factor that out from this first term, what's left is minus x squared minus y squared minus z squared. And when we factor it out from this second term here, what is left is this times this times this, which is minus 3. Notice that we have a minus here, and so it becomes plus, and when we multiply this times this times this, we get plus 3x squared, and then everything is still divided by that same denominator, so let me write that in. If we clean this up a little bit, this part right here, we're going to get a little bit more concise expression. So let's do that on the next blackboard. Notice that when we got v sub xx, the variables that were not x had a minus sign in front of them to the second power in the numerator, and the variable that was the one we're taking the second partial with respect to had a coefficient of 2 and a positive sign with respect to it. So it should make sense that if we follow the same process, we would get these two expressions for v sub y and v sub z. So if we look at these three expressions, recall that what we are trying to do here is add these three partials together, v sub xx plus v sub yy plus v sub zz, and see if they're equal to 0. So we look at what we have here. And we notice that we have a 2x squared, a 2y squared, and a 2z squared in the numerator. But we also have negative 2x squared, negative 2y squared, and negative 2z squared. And so that gives us a 0 in the numerator, and therefore we have that this function v right here satisfies the Laplace's equation, because, and we show that v sub xx plus v sub yy plus v sub zz is 0. In these next couple of examples, we want to look at mixed partial derivatives. That means with respect to x, then y, or with respect to volume, and then with respect to temperature, and then reverse that, with respect to temperature, then volume. We actually find out that in all the application cases we will be considering, or you will be considering, chemistry applications, the mixed partial derivatives are equal. So let's first start with the general case with this function f of xy, and let's take the partial with respect to x, so we'd be holding y constant, so we would get 2xy squared. We would not get any from this term since everything is with respect to y, so that derivative, or that partial, is a constant. The partial with, I'm sorry, I wrote the problem down wrong. This is an x squared here, not a y squared. So when we are taking the partial of the second term, we take the partial of e to the x squared and get the derivative of the exponent times the function itself times y, which is just acting as a constant. And then when we take f sub y, holding x as a constant, we get 2 yx squared plus, and then here we're taking the derivative of this term right here, holding x as a constant, so everything here is a constant, and so what we get is the derivative of the y part is 1, and then we just get the constant that remains, e to the x squared. And now let's take second partials, the mixed second partials. So x we've taken, and then we're going to take with respect to y, and we get, when we take the partial of this term right here, we're holding x constant, so we get 2y. And then when we take the partial of this term right here, holding x constant, we essentially just get all of, or we essentially do get all of this, because that is the constant. Now when we go to take f sub y, and then with respect to x, and we look at this term right here, we're treating x as a constant. I'm sorry, we're treating y as a constant. Before we do for f sub yx, let's go back to f sub xy, where we're holding x as a constant. So we're taking the partial of this term. That would be the 2x is acting as a constant, and we're taking the partial with respect to y of the 2y. So that does give the 2y part, but it is multiplied by 2x. So this should be times 2x right here. And so now let's find f sub y with respect to x, identifying what is held constant over here in f sub y. So the x squared is So since we're doing the partial with respect to x, this time the 2y is a constant, and we're only taking partial with respect to x of the x squared, and so that gives us 2y times 2x, and then when we go to take the partial of this with respect to x, we just use the regular rule for that, for taking derivatives of exponential functions, so it's e to the x squared times 2x. And if you look at these two expressions, this and this, you can see that they are equal, or the mixed partial derivatives are equal. So let's do an example where we use the mixed partials being equal to develop an important, very important relationship, thermodynamics relationship. So let's start with defining the letter capital S to be entropy, capital P is pressure, A is Helmholtz energy, and entropy would be defined as the partial of energy with respect to time with a negative sign out front, and pressure would be defined as the negative partial of energy with respect to volume. So if we take the partial of the entropy with respect to volume, then that's going to give us the second second partial of the energy, and it is first with respect to time, second with respect to volume. If we take the partial of the pressure with respect to temperature, we're going to get the negative of the second partial of the energy. First we had already taken it with respect to volume, now we're taking it with respect to temperature. But since all of these functions are continuous, and back to our previous slide, mixed partials are all equal when the functions involved are continuous, which they are. Functions and the derivatives are continuous, which they are. These two expressions, where they only differ by the order in which you take the partials, this one t first and v second, this one v first and t second, they are equal because of the equality of mixed partials. And from that we get that partial s, partial v equals partial p, partial t, partial s, partial t, partial v equals partial p, partial t. That relationship is a very important relationship, and it is known as Maxwell's equation. So the equality of mixed partials and thermodynamics principles gives us Maxwell's equation. We're going to conclude or wrap this video on functions of second variables, and on the next video take a look at take a look at more properties of functions of several variables involving derivatives and other properties related to derivatives.